Okay, so it's 4-5. Let's start. I'll share my screen. Is my screen visible?
Yeah, it's visible.
Yeah. So first we'll quickly recall what we saw in this week. So in this week we saw what a Boolean circuit is. So a Boolean circuit is a directed acyclic graph whose leaves or inputs are labeled by variables and constants 0 and 1, and its internal nodes are labeled by AND, OR and NOT gates, and it has one output gate and computes a Boolean function naturally. So for example, here's one Boolean circuit. So let's say its inputs are x1 and x2. Then there is a NOT gate and AND gate. There's another NOT gate over here. Another AND gate over here, and then there is an OR gate. So this is an example for Boolean circuit, and you can see that this circuit computes x1 complement and x2, or x2 complement and x1. So this computes the exclusive OR of the two. So then there are two complexity measures associated with a circuit. The first is the size of the circuit, which is equal to the number of vertices in the directed acyclic graph of the circuit, and there is a depth of the circuit, which is equal to the length of the longest path from the output gate to any input of the circuit. And now what we'll do is we'll work with circuit families, and a circuit family is a collection of circuits Cn for every n greater than or equals to 0. So we say that a circuit family script C decides a language language A, if for all strings of length n, for all strings x of length n, Cnx equals to 1 if and only if x is in A. And size of a circuit family is defined naturally. So the size of a circuit family C is S of n if for all n greater than or equals to 0, the size of the circuit Cn is at most S of n. And then we define this complexity class size S of n, which is a class of all languages A, so that A is decided by a circuit family of size order Sn. Then you saw this theorem which proves a lower bound on the size of any Boolean circuit computing a certain Boolean function, in particular a random Boolean function. And what the theorem says is that there exist languages not in size 2 to the n over 10 times n, and in particular a random language would satisfy this property. Then you saw the size hierarchy theorem, which says that if n is less than or equals to 25 times n times fn, and this quantity is less than or equals to gn, which in turn is upper bounded by 5 over 2 times 2 to the n, then the class size of fn is strictly contained in the class size of Gn. And then you saw the definition of the class P/poly. So it's a class of all languages that can be decided by polynomial size circuit families. That is a union over C greater than or equals to 1. The class is size n to the C. And it's easy to see that P is contained in P/poly. So we might want to ask if P equals to P/poly or not. However, it's known that P/poly also contains some undecidable languages, in particular the unary version of the Holt language, and so P is definitely not equals to P/poly. Then you also saw the Karaplipton theorem, which says that if NP is contained in P/poly, then the polynomial hierarchy collapses to sigma 2. and since it's not believed that the polynomial hierarchy collapses, we also don't believe that NP is contained in P/poly. Then you saw an equivalent way to define P/poly, and for that you saw what TMs with advice are. So a Turing machine with advice is a Turing machine that takes two inputs, a string x and an advice string a size of x. Now a Turing machine that takes advice looks a lot like a Turing machine that takes a certificate, but there is a crucial difference between a certificate and an advice, and the difference is the following. So for every string x, a certificate can be different, but for all strings of the same length, the advice string is the same. And Turing machines with advice are a way to model Boolean circuits. Then you saw the definition of the class d time Tn/an. So this means d time Tn with an bits of advice. So it's the class of all languages decided by Tn time deterministic Turing machines with an bits of advice. And so now the class P/poly, in particular why we write P/poly starts making sense, because it's just a class of all languages decided by polynomial time Turing machines using polynomially many bits of advice. So yeah, P/poly is the union over C and D of d time n to the C / n to the D. Finally, you saw the definitions of the classes NC and AC. So the class NC superscript I is the class of all languages decided by a circuit family Cn n greater than or equals to 0, so that the size of Cn is poly n, the depth of Cn is order log to the in, and Cn only contains and or gates of fan-in2 as well as NOT gates. And then you saw the definition of the class AC, which is very similar to NC, but it's a class of all languages that are decided by a circuit family Cn, such that size of Cn is poly n, depth of Cn is order log to the in. So far it's the same as NC, but here's the difference. However, Cn can contain and OR gates with arbitrary fan-in. Oh, so there is a typo over here, this shouldn't be there. Fan-in2 with arbitrary fan-in and NOT gates. So it's clear that NCI is contained in ACI, because what you can do with circuits with bounded fan-in, you can also do with circuits with arbitrary fan-in. So we know that NCI is contained in, again it's a typo, NCI is contained in ACI, which is contained in NCI plus 1. And the class NC is defined as union over I greater than or equals to 0 NCI, and class AC is defined as union over I greater than or equals to 0 ACI. Now NC equals to AC because of this relationship, because ACI is contained in NCI plus 1. So that's for the recap. So now let's move to the problems. The first problem is, how many distinct symmetric functions are there from 0, 1 to the n to 0, 1? The options are n square, 2 to the n, 2 to the n plus 1, and 2 to the n. So would you like to guess the answer to this, or do you know the answer to this question? Okay, so the answer to this is 2 to the n plus 1. Let's see why. So let's work it out. Yeah, a function f from 0, 1 to the n to 0, 1 is said to be symmetric if for all strings of length n and all permutations in Sn. So Sn is a set of all permutations over set of all permutations of the set 1 to n. So a function is said to be symmetric if for all x in 0, 1 to the n and sigma in Sn, f of x is equal to, so let's say the bits of x1 are x to the x1 to xn. So if f of x1 to xn is equal to f of x sigma 1, up to x sigma n. So what this says is that even if you take the input and permute the bits in it, the function should remain the same. So this implies that if x and y in 0, 1 have the same number of zeros, and since the strings are 0, 1 strings, if the strings have the same number of zeros, they also have the same number of ones, then f of x is equal to f of y. So is this claim clear? Why this implies this?
Yeah.
Yeah. So if this is the case, so then let x0, or yeah, let me write it like this. So then for I from 0 to n, let x0 be the string. Oh yeah, let xi be the string. Yes, let xi be the string. 0, 1. Then f is completely determined by its values at fx0 to fxn. So basically, to define x, we only need to define x at these strings, and for all I, fxi, there are two possibilities for fxi. Fxi can be 0 or 1. So the number of functions is equal to 2 to the n plus 1. Why? Because we have to so to define a function we have to fix these n plus 1 numbers. It's n plus 1 because the indexing starts at 0 and goes to n, and for each of these numbers we have two possibilities. It's either 0 or 1. So it's 2 times 2 times 2 times n plus 1 times, so it's 2 to the n plus 1. So the number of symmetric functions from 0, 1 to the n to 0, 1 is 2 to the n plus 1.
Yeah.
Yeah. So the second problem is, how many distinct monotone functions are there from 0, 1 square to 0, 1? So do you know what a monotone function is?
Bitwise xi will be less than yi.
Right. Then yeah. Then what?
So I mean xi should be, if it is 0, I
Right.
mean xi cannot be 1 and yi cannot be 0 simultaneously.
Okay. Right. Yeah. So yeah, I see what you're saying. So okay. So the answer to this is 6, and let's see why. So yeah, a function f from 0, 1 to the n to 0, 1 is said to be monotone if x greater than equals to y implies f of x greater than equals to f of y. Okay, so x and y are strings. So what does it mean to say that x is greater than equals to y? It means the following. If x if x equals to x1 to xn and y equals to y1 to yn, then x is greater than equals to y if for all I, xi is greater than equals to yi. So what this definition is saying is, if bitwise xi, if bitwise the string x is at least the string y, then it is not possible that f of x is 1, sorry, f of x is 0 but f of y is 1. So is this definition okay?
Yeah.
Right, yeah. Okay, so and we want to find the number of monotone Boolean functions from 0 comma 1 square to 0 comma 1. So let's enumerate them. So there are 4 possible strings: 0 0, 0 1, 1 0 and 1 1. Now for 0 0 we have two possibilities. F of 0 0 can be 0 or 1. Let's first try 0. Now since f of 0 0 is 0, f of 0 1 also has two possibilities. It can be 0 or 1. Let's try 0 first. Similarly for f of 1 0 we again have two possibilities, 0 or 1. So let's try 0 first, and same with f of 1 1. So again let's try 0 first. So this gives us one monotone function, the all zeros function. Then for f of 0 0 let's still try 0. Now for f of 0 1 we had two possibilities, 0 and 1. We have already tried f of 0 1 is 0, so let's try f of 0 1 is 1. Now f of 1 0 can again be both 0 and 1, because 1 0 is not greater than 0 1. So f of 1 0 can still be 0. But now let's look at f of 1 1. Now 1 1 is greater than or equals to 0 1. So since f of 0 1 is 1, f of 1 1 has to be 1. So f of 1 1 cannot be 0 in this case. So f of 1 1 is 1. This gives us one more monotone function. Now for f of 0 0 and f of 0 1, both can be 0, and now f of 1 0 can be 1. So let's try that case. Now f of 1 1 is greater than f of 1 0. So since f of 1 0 is 1, f of 1 1 also has to be 1. So this gives us one more monotone function. Now I skipped a function actually. So what we can do is, for f of 0 0 can be 0, f of 0 1 can be 0, f of 1 0 can be 0, and f of 1 1 can be 1. So this gives us one more monotone function. And now what we can do is, f of 0 0 can be 0, f of 1 0 0 1 and 1 0 both are 1, and now f of 1 1 is forced to be 1 because f of 1 1 is because 1 1 is greater than 1 0 as well as 0 1, and both of them are 1. Finally, if f of 0 0 is 1, then all others have to be 1 because all these strings are greater than 0 0. This gives us 6 distinct monotone functions. These are all the functions we get.
Yeah.
So now the next couple of problems are just recall problems. So suppose f of n is equal to 10 times 2 to the n, and g of n is equal to 300 times n times 2 to the n. Does the size hierarchy theorem implies that size of fn is strictly contained in size of gn? So would you like to guess?
That inequality actually.
Right. Okay, so yeah, it doesn't, because in size hierarchy theorem you need gn to be at most 5 over 2 times 2 to the n, and in this case gn is like strictly asymptotically greater than 2 to the n. So size hierarchy theorem does not imply this. So even though the functions fn and gn satisfy the relation that you need for the size hierarchy theorem, because of this condition that gn must be greater at most 5 over 2 times 2 to the n, we cannot use size hierarchy theorem over here. Yeah, so why can't I? Yeah. So the next problem is, in the model of Turing machines that take advice, which of the following is the most accurate statement? There is a fixed advice string for all inputs. For each input length, there is an advice string corresponding to that length. For each distinct input, there is an advice string corresponding to that input, and the advice string is a randomly chosen string that is generated afresh from a distribution for each one of the TM. So which is the most accurate statement?
Yeah, I think B.
Yeah, for each input length, there is like just one advice string. Yeah, that's correct. The fifth problem is, which of the following statements are currently known to be true, and select all that apply. So the statements are, all the languages in P/Poly have efficient algorithms. P/Poly contains undecidable languages. There are languages in P/Poly that require exponential size circuit families in order to decide, and P/Poly contains all the unary languages.
I think B and D.
Yeah. So the answers are B and D. And now, first of all, B immediately implies that A is not possible, because you don't even have algorithms for undecidable languages, let alone efficient algorithms. And C essentially says that P/Poly contains, so this essentially says that P/Poly has a hard function. So P/Poly has a hard function which we still don't know. Oh wait, no. So yeah, C says there are languages in P/Poly that require exponential size circuit families in order to decide, but this is not true because the definition of P/Poly is poly-size circuits. So this is like false from the very definition of P/Poly. And P/Poly does contain unary languages. Now you might have seen this in the class, but let's quickly go over the proof again. So the proof is the
Yeah,
following.
actually, I did not understand that unary while proving that unary languages in P-poly, we use the AND gate.
Right.
So, but I don't understand why AND gate.
Okay, so basically, yeah. So if A is a unary language, there is only one unary string of length n, right? It's 1 to the n.
Yeah.
Right. Now, only one of the two things are going to happen. Either 1 to the n is going to be in the language, or 1 to the n is not going to be in the language, right?
Yes.
Now, suppose 1 to the n is in the language. Because we are allowed to have one circuit for each and every value of n, we are allowed to create a special circuit that recognizes just 1 to the n, right?
Yeah.
And one very such simple circuit is just take AND of all the input bits, right?
Yeah.
Right. So what we do is, whenever x like 1 to the n is in A, this simple circuit of it takes AND of all the gates, all the inputs works. Now I agree, there can be other circuits as well that work, but this is a very simple circuit that does work, so we will go with this. And if yeah,
okay, so it's just a kind of, it exists, so we can give one existence,
right?
One circuit. Yeah.
Yes, I mean other circuits might also exist, like you can always create some complicated circuits that also accept 1 to the n. Yeah. Now another possibility is that for a particular n, 1 to the n is not in A. In this case, we again create a circuit that does not accept 1 to the n, which is just take AND of all the inputs x1 to xn. That AND would be 1, fit it into a NOT gate, so it would be 0. So what we have done is, for every n, we have created a circuit Cn which accepts 1 to the n if and only if 1 to the n is in the language, and does not accept 1 to the n if it's not in the language, right? So the circuit, the circuit family Cn clearly decides A, and the size of Cn is also poly n because it's just one AND gate, or one AND gate and a NOT gate, right?
Yeah.
So A is in P/Poly.
Yeah.
And this was for any unary language. We did not use any special structure of A, right?
Yeah.
And there is a, as you might have seen in class, there is a unary language uHalt, which is a unary version of Halt, which is also in P/Poly because it's unary, but it's undecidable, right?
Yeah.
Yeah. So
but in uHalt, actually we had the binary description and we changed that binary description into unary description.
Right.
But at the same time, we just claimed that it is undecidable.
Okay. Okay. So
So, I mean, the undecidability part, I'm not sure. Uh, I mean, has it been proved or not?
okay. Oh, the proof is very simple. Okay. So you are worried about decidability, right? So you don't care
Yeah,
about the running time
yeah.
of the algorithm, right? So
Yes,
all
yes.
you need to worry about is whether an algorithm exists or not. Even if it's exponential time, you are fine, right?
Yes,
And
yes,
this
yes.
observation gives you a very simple proof that u halt is also undecidable. Why? You are given u halt, right?
Yeah,
So you are given a string 1 to the n.
yes.
Convert it into binary.
Yeah.
Oh, sorry, wait. No, you want to reduce halt to this, right? So
Y-
suppose you are given a. So what would you be given in a halt, right? You would be given a
In
string in binary, right?
Yes, yes. The
Convert it to
Turing
unary,
machine's description. Yeah.
right? Convert it to unary
Yes.
and see if that unary string is in u halt or not,
Mm-hmm.
right?
Yeah.
Yeah, so how have we defined u halt? It's exactly 1 to the n is in u halt if the corresponding binary string is in halt, right?
Yes, yes,
So if you
yes.
had an algorithm for u halt, you would have an algorithm for halt as well. Sure, the running time would be terrible.
Oh,
Yeah,
oh.
but you're not worried about the running time. You're just worried about whether an algorithm exists or not. So you can do this. So this is sort of an exponential time reduction, right? Instead of a poly time reduction.
Mm-hmm. Yeah.
But that's still fine because we don't worry about we don't care about the running time.
Yes,
Yeah.
yes.
So basically, whenever a language is undecidable, its unary version would also be undecidable because of the exact same argument.
Yeah.
Yeah. Yeah. So the next problem is which of the following statements captures the statement of the Carr-Lipton theorem most accurately? The options are A. SAT does not have polynomial size circuits. Option B. If SAT has polynomial size circuits, then SAT has a polynomial type algorithm. If SAT has polynomial size circuits, the polynomial hierarchy collapses and the SAT has polynomial time circuits.
I think C.
Yeah. So what C says is if set has polynomial size circuits and polynomial hierarchy collapses. And what Carr-Lipton theorem says is that if NP is contained in P slash poly, then then polynomial hierarchy collapses. But since SAT is NP complete, SAT having polynomial size circuits is exactly the same as NP being in P slash poly, right? So these
Yeah.
two statements are equivalent. Okay, not exactly equivalent because this statement only says that the polynomial hierarchy collapses. Carr-Lipton theorem is a little more explicit. It says that the polynomial hierarchy collapses to the second level. But that's the only
Second.
difference.
Yeah.
Yeah.
Yes, yes.
So the next problem is which of the following facts is crucially used in the proof of the Carr-Lipton theorem? Set is reflexive, set is anti-symmetric, set is transitive, and set is self-reducible.
D.
Yeah. Yeah, it's set is self-reducible. Again, this is a recall question. There is nothing to explain over here. Yeah, so the next problem is NAND is a Boolean function that returns a 0 if and only if all the input bits are 1. So it is a negation of the AND gate. So a NAND gate is a negation of the AND gate. Now suppose we define a new complexity class called NAND NC to the I to be identical to the definition of NC to the I, except that instead of allowing OR, and NOT gates with OR and AND gates of fan in 2, we only allow NAND gates of fan in 2. Which of the following statements is the most accurate one? NAND NC to the I is contained in NC to the I. NC to the I is contained in NAND NC to the I. NC to the I and NAND NC to the I are exactly the same, and neither is a subset of the other. So what's the answer to this one?
I think C.
Yeah, C is correct. Let's see, 5. So yeah, okay. So let's do it in 2 claims. So if a language L is in NAND NC to the I, then there exists a circuit family script Cn such that, or so there exists a circuit family that decides L such that for all n, size of the circuit Cn is equal to poly n, its depth is order log to the in, and Cn only contains two input non-gate AND gates. Two input NAND gates are just NAND gates with fan into, right? So what we'll do is, using this circuit Cn, we'll construct a new circuit C prime as follows. We'll replace every NAND gate by an AND gate and a NOT gate. In particular, if we have NAND of F1 and F2, so over here F1 and F2 are some inputs, like they might be Boolean functions. So if the NAND gate that you are looking at is directly connected to two input gates, then F1 and F2 would be variables. But if the NAND gate is connected to, let's say, two other NAND gates, then F1 and F2 might be Boolean functions. Okay, so what we'll do is, NAND F1 and F2 would become NOT of F1 and F2, and these two are exactly equal because of the definition of the NAND gate. So because of the definition of NOT, Cn and C to the n prime are equivalent circuits. So in particular they compute the same function. So we have this new circuit family C prime n, which also decides the language also. Decides L. Now all we need to do is to show that this circuit family is also an NC1 circuit, NCI circuit family. Now notice that C prime n only contains two input NAND gates and NOT gates. So that condition is satisfied. Now what's the size of C to the n? The size of C prime n is less than or equal to 2 times the size of C to the Cn. Why? Because what did we do to create C prime n? We took each and every gate in Cn and replaced it with 2 gates. So the size blows up by at most a factor of 2. So, yeah. And what about depth? So what did we do? So we took a NAND gate and replaced it with a depth 2 circuit, right? So this circuit, not of F1 and F2, is a depth 2 circuit. At the bottommost level you have F1 and F2 and then a NOT gate on top of it. So it's depth 2 circuit. So the depth of C prime n is at most twice the depth of Cn. So size of C prime n is equal to poly n, and depth of C prime n is still order log to the I. So in particular, this family of circuit C prime n is also a family of NCI circuits. So L is in NC to the I. This proves one direction, and since this is true for every language in NAND NCI, this means that NAND NCI is an NCI. So this proves one direction. Now let's prove the other direction. Okay, so if L is, the proof is almost, the overview, the outline of the proof is the same, but let's look at it. So if L is an NCI, there exists a circuit family no, let me write Cn over here. There exists a circuit family Cn n greater than equals to 0 such that size of for all n greater than equals to 0, size of Cn is equal to poly n, depth of Cn is equal to order log to the In, and Cn only contains two input or at AND gates and NOT gates. Further, this family decides. Now again, what we'll do is we'll use this family to construct a family of circuits C prime n. So construct C prime n as follows. Number 1. So suppose that C as a gate, not F, replace this gate by the gate NAND F, 1. Now I claim that not F and NAND F, 1 are the same. Why? Suppose F is 0, then not F is 1. And what is NAND Fn1? So NAND Fn1 is the negation of the AND of 0 and 1. Now AND of 0 and 1 is 0, so the negation of it is 1. So if F is 0, then NAND F, 1 is 1. Similarly, if F is 1, And what is NAND f comma 1? It's the NAND of 1 comma 1, which is 0. So NAND f comma 1 is exactly the same as the gate not f. Similarly, we'll replace the gate f1 and f2. So what is f1 and f2? It's not of NAND f1 and f2. But we have already seen what like how to implement this NOT gate using just the NAND gate. So if over here you put NAND f1 comma f2 in place of f, you get NAND so this is how we'll implement an AND gate. And what we'll do for the OR gate is the following. If we have f1 or f2, replace it. Okay, so what is f1 or f2? Yeah, so f1 or f2. Okay, instead of this, let me write an equality over here everywhere. So what is f1 or f2? From De Morgan's law, we know that f1 or f2 is the negation f1 and negation f2. Okay, so now we know how to, okay, so now let's look at this bracket. What is inside this bracket? This bracket is exactly NAND of negation f1 and negation f2. And so now the only gates that we are left which are not NAND gates are these three NOT gates, but we know how to implement them. So this is equal to NAND of f1 comma 1 and NAND of f2 comma 1. Let me write this on the next page. Not NAND, not f1, not f2. Oh, what happened? Yeah. And now I know how to implement all of these NOT gates. So let me do this step by step. That would be easier. It's NAND of, so let me implement this NOT gate. It's NAND f1 comma 1 and this NOT gate. It's NAND f2 comma 1. So we are still left with one NOT gate which we can also remove by using a NAND gate. NAND of this entire thing comma 1. This entire thing comma 1. Yeah. So is this fine?
Yeah.
Yeah. Okay. And so now, because not f is exactly the same as this, f1 and f2 is exactly the same as this, and f1 or f2 is exactly the same as this, Cn and Cn prime are equivalent circuits. So the circuit family C prime n greater than equals to 0 decides well. Now let's compute. Okay, now also everywhere in C prime n we have used NAND gates, and those NAND gates are finite at most 2. So C prime n NAND gates. So if we can show that the size of C prime n is poly n and its depth is order log I to the n, we would be done. So let's compute the size of C prime n. Okay, so what did we do? To implement one NOT gate, we only needed one NAND gate. To implement an AND gate, we needed 2 NAND gates. And to implement a NOR gate, we needed 1, 2, 3, 4 NAND gates, right? So to implement any gate, we needed at most 4 NAND gates. So we would have replaced every gate in Cn with at most 4 gates. So that's 4 times size of Cn, less than or equals to 4 times size of Cn plus 1. This plus 1 is because I'm using this 1 somewhere, right, at a lot of places. So I might have to add an extra input gate or input node which is 1. So earlier the input of Cn might have been just x1 to xn. Now it's x1 to xn and 1. So that's why this extra 1 is coming. And what is depth? Okay, so to implement a NOT gate, we only needed one NAND gate. So a circuit with depth like just 1. To implement an AND gate, we needed a circuit with depth 2 because we are using 2 NAND gates. And to implement an OR gate, we needed like a circuit with depth 3, because even though we are using 4 NAND gates, these 2 NAND gates can be computed in parallel together. So the depth of this circuit is 3. So depth of C prime n is at most 3 times depth of Cn. Therefore size of C prime n should write equals to poly n, and depth of C prime n is equal to order log to the I n. So let me write over here. So L is in NAND NC to the I, and since this is true for all L's in NC to the I, this proves that NC to the I is in NAND NC to the I. So since both are contained in each other, they are exactly the same class. Yeah.
So this would be true for any universal gate.
Right. You can also do the same thing for example, for NOR gates.
Yeah.
So consider the language mult8 that consists of all n-bit integers x equals to x1, x2 up to xn that are a multiple of 8. What is the smallest value of I for which mult8 is in NC to the I? So would you like to guess? Okay, so the I haven't written the answer. Yeah, so the answer to this is it's 0, and the reason is the following. So x equals to x1 to xn is a multiple of 8. This is the same as saying there exists y, a natural number, such that x is equal to 8 times y. If I write this in binary, it's 1000 times y, right? Now if you now y is an integer, so if you multiply this out, you would see that this is the same as saying that the last 3 bits of x I, that is xn minus 2, xn minus 1 and xn are 0. Okay, so now we know that x is in the language if and only if xn minus 1, xn minus 2, xn minus 1 and xn are 0. This gives us a very simple circuit. So its inputs are the n bits, and the circuit is this. So we first compute the negation of xn minus 2, xn minus 1 and xn, then compute the AND of the first two numbers and then the end of the second two numbers, and this is our circuit. Okay, so now when would the circuit output 1? So this circuit would output 1 if and only if the outputs of all of these 3 gates are 1, right? And the output of all of 3 gates would be 1 if and only if xn minus 2, xn minus 1, xn are 0. But in that case we saw that x is divisible by 8. So this is a very simple circuit that checks whether a number is divisible by 8 or not, and the size of this circuit is clearly poly n, and its depth is what? Like, depending on how we define the length of a path as the number of nodes or the number of edges, it's 2 or 3. Yeah, so the depth is constant, the size is polynomial, so this means that the language is in nc to the I, sorry, nc to the 0. So the answer is 0. Yeah. So the next problem is, which of the following statements is or are currently known to be true? Select all that apply. The first statement is AC2 is in NC2. The next statement is NC2 is in AC2. Third statement is AC2 and NC2 are exactly the same class, and the fourth is AC2 is not equals to NC2. So what's the answer to this one?
Maybe B.
Yeah, the answer is B. So whether or not AC2 is equal to NC2 is an open problem. Yeah, so that rules out this and this as well, because if this were true, then A and B would imply that C is true. Yeah, oh, yeah, that shouldn't be over here. So the next problem is, what is the value of I for which we know that log space uniform NCI is contained in L, is contained in Ln, and L is contained in log space uniform NCI plus 1. So do you know what a log space uniform class is?
Yeah, so the Turing machine writes a description of the circuit with the constraint of log space function.
Right, yes. Yeah, so this shouldn't be over here, this should be on the next slide, but yeah, the answer is 1. Let's see why. So suppose that A is in NC1, then there exists a circuit family Cn n greater than or equals to 1 that decides A such that size of Cn is poly n, depth of Cn is order log to the In, and Cn only contains and or gates of n into and not gates. Also, because we are looking at log space NC1, there exists a deterministic log space machine M, so that M on input 1 to the n outputs a description of Cn. So this is what A in NC1 gives us. Now what we want to do is we want to show that this, if A is in log space NC1, then A is also in L. So how will we do that? what we'll do is the following. We create a Turing machine M prime which does the following. When it is given an input string x of size n, it uses M to first generate the circuit Cn and then evaluates and outputs Cn of x. So clearly M prime decides A. Is this fine?
Yeah.
Right. But now we need to show that M prime is a log space machine. The problem is the description of Cn can take more bits than order log n, but there is a way to get around that problem. What we'll do is the following. Instead of using M to write the entire description of Cn on the work tape of M prime, we can use M to compute a bit of the description of Cn whenever we require it to evaluate Cnx. So this is like implicit log space computation, something similar to what we did to show that if a language A reduces to language B in log space and language B is in L, then language A is also in L.
Yeah.
So is this clear how we can compute Cn by without explicitly writing it down?
Yeah. So
Right.
we'll whenever required and whatever is required, only that much is written.
Right. Yeah. So we can basically compute it bit by bit and use that to compute Cnx. The combined machine M prime now runs in log space. Yeah, so M prime is a deterministic log space Turing machine, and so A is in L. Thus we have shown that NC1 is in L. However, we already know that L is contained in NL, so we have NC1 is in so we have log space NC1 is in L is in NL. But now what we want to do is we want to show that NL is contained in log space uniform NC2. So recall that a language path defined as G, S, T, so that G is an undirected graph and there is a path from node S to node T in G. This language is NL complete and this language is in log space uniform AC1. But log space uniform AC1 is in log space uniform NC2. So path is in log space uniform NC2. But since path is NL complete, this means that NL is contained in log space uniform NC2. Yeah, so the answer to the question is 1, because if you put 1 over here, you get log space uniform NC1, L, NL, log space uniform NC2. Yeah. So is this fine?
Yeah.
Yeah. So this was all that we had for today. So if you have no other questions, we can meet next week.
Yeah.
Yeah.
Thank you.
Thank you.